Hi, my name is Yidong, and today I'm going to present our work identifying and analyzing the pitfalls in GNN systems. This is a joint work with Arnab, Saima, and my advisor, Dr. Kumar. So first, as we know that graph neural networks are widely used across different applications, such as a social network, biomedical, etc. So based on that, many GNN models are proposed, such as the GCN, GAT, and GIN, etc. And after that, many system-based baseline are proposed, such as the deep graph library from the Amazon and the PyTorch geometric, which build upon on the PyTorch. So after that, many conferences, some research work, they propose the GPU-based system optimizations. However, after we analyzing those GNN systems, we identify that there are existing some pitfalls in these GNN systems, which led us to re-examine some existing system optimization in GNN systems. And it also motivates our solution GRAPHPY, which should be treated as a new proper reference systems. So here is an overview of the whole papers. We actually first talking about 3 levels of the pitfalls. After that, we introduced our solution GRAPHPY, which should be treated as a correct reference systems. And also in the paper, we also provide some quantitative analysis and evaluations to prove that those pitfalls is important. So here is the outline of today's presentations. So I will first talk about the background, then discussing those pitfalls we identify, and then I will talking about the evaluations. So here is the background. So as we know that for the graph neural networks, we need to use a graph as input. So given a sample graph, the baseline deep graph library, they actually use 3 different formats to represent the graphs. So the COO format, it is more like an age list. So the first array represents the row ID, the second array represents the column ID, and the third array represents the age feature. The CSR represents the graph, and the CSC format represents the graph transpose. The A here means the agency matrix. Actually, it is a graph. It's just like a graph. So you can see that for the CSR and CSC, they are very similar with each other. So the only difference is the age ID are different, and the age weight, they are actually in the reverse orders. So for our solution, the storage format in our solution is very similar to the DGL, but we made a little bit modifications. So what we made is we ran the COO from the CSR way to enable better data locality. So you can see here, given these 4 ages, they are all coming from the same node ID 2. However, in the original DGL format, COO format, you can see those 4 ages, they are actually scattered away. Scattered away. So as we know that for GNN, they actually need to use the sparse kernels for its computations. Actually, in total, they use 2 types of kernels. One is SPMM, which will output a vertex level output. Another one is the SDDMM, which will generate an age level output. So now let's discussing the pitfalls we identified. So the first pitfall is a framework level pitfalls. Actually, they have 2 types of pitfalls in here. So the first type is a framework runtime overhead, which we find that for the private GNN systems, they do the evaluation majorly or exclusively on a small data set. However, we show that the evaluation on small data set leads to pitfalls because it only represents the framework overhead, not the actual GPU runtimes. So here is a simplified timeline figure we got from the PyTorch profile for 1 training iterations. So what we do is we run the DGL on the GCN model on the core dataset, which is small. So you can see if we coming from the device side, between different GPU kernel, they actually have a very large and frequent idle time, right? So in here you can see it is very clear that the overhead time is much larger than the GPU runtime. So in the paper, actually, we propose the methodology of how to measure the overhead, which is the CPU time minus the CPU wait for the GPU times. The K here represents the number of the training iterations. In the appendix of the paper, we propose more detailed explanations. So here we plot two figures to show that the relationship between the overhead and the graph size. So you can see when the graph size, when the H count is smaller than 4 million, the overhead time is much larger than the GPU time. And of course, you can see on the right part, the overhead is almost equal to the training runtime. So even when the H count going to around the 60 million, the overhead time will be similar to the GPU times. So which shows that the training runtime on small data sets actually dominated by the framework overhead. So actually what we do is we plot the training runtime and the overhead time across different GNN systems on different GNN models across different data sets to show that actually the framework runtime, the framework overhead is prevalent. So the takeaways here is first, the training time comparison on small data set is not the GPU runtime comparison. Second, many of them are actually slower on the middle-sized data set, which I show on the next slide. So you can see here is on the middle-sized data set, you can see actually for some GNN systems, such as the TC GNN and the Maris GNN, those works, they are much slower than the CoolSparse, which is a vendor library coming from NVIDIA. And of course, our solution GRAPHPY are the fastest one. The second type of the framework level pitfalls is the memory overhead. So we find that the baseline deep graph library, it runs out of memory on the middle-sized data set frequently. The reason is because it uses a non-standard integration with a PyTorch for its tensor memory management. So how to prove that? So what we do is we first run the DGL's SPMM kernel to measure its memory. So which means for this one, actually it includes the memory, the framework and it includes the framework and the CoolSparse, which take 13 gigabytes. Then what we do again is we just run the CoolSparse SPM kernel from NVIDIA directly, which only need to take 1 gigabyte. So then we can do a math here, so we can calculate, to show that the memory overhead is around 12 gigabytes. So this memory overhead actually first force the evaluation on a small data set, and it will also inflate the memory saving result by the prior works. So our solution GRAPHPY actually fixes those pitfalls, and you can see actually it achieves significant memory saving over the DGL. So the recommendation here is first, when we're trying to evaluate the training runtime, we should use a middle-sized data set if possible. Otherwise, we should first try to prioritize optimizing the framework overhead. And also, the second suggestion is compare with our reference systems, GRAPHPY. So then another type of the pitfalls we find is the evaluation pitfalls. We find for many GNN systems, actually there is a clear trend for not measuring the accuracies. However, those works, they assume that they use the semantic preserving model, which means the model is the same, the training algorithm is the same. In that way, the accuracy should be the same, right? However, when we write extra code to enable the training accuracy for some of these GNN systems, we find that actually some of them have the abnormal training accuracies. So then, based on that, we did a code study of their code. Actually, we summarized several system design pitfalls, which leads to these abnormal accuracies. But the most important things we want to show that is even we can fix those pitfalls. However, after we fix those pitfalls, those performance optimization will not work anymore. The first system design pitfall is omitted the state tensors. State tensors is some tensors which produce in the forward, but it's needed to be used in both the forward and backward. However, for some GNN systems, prior works, what they do is they just implement the forward computation and use it to simulate the total end-to-end training. Some other work, they do the kernel fusion, however, without producing the state tensors. The second system design pitfall is missing or inefficient parts matrix transpose. So as you can see here in the forward part, we need to use the graph. However, in the backward part, we need to use the transpose graph. However, we find that for many prior works, what they do is they actually did not consider this requirement. What they do is they just use the SPMMVE in place or instead of the SPMMVE transpose kernel, which means they did not consider the requirement of the transpose graphs. Some other work, what they do is they use an additional kernels to first transpose the graph inefficiently and did not even compare with the NVIDIA CUSPARS SPMMVE transpose kernels. So here is like an evaluation. What we do is we try to, the eShuffle here represents the graph transpose kernel. So you can see after we fix the pitfalls, so for some of those GNN systems, which means we need to use the total time for the SPMMVE transpose kernel will be the blue plus the yellow time. You can see many of them will be even much slower than the CUSPARS library, which is a vendor library coming from NVIDIA's. And of course, our GRAPHPY is the fastest one. The last system design pitfalls is the incorrect order of backward operations. So we find that many prior works, they actually implement the backward operations in wrong order, and they're missing some backward operations. And in the paper, we have more detailed discussion of why those pitfalls are fixed. The performance optimization will not work anymore. So the recommendation here is first, measure the training accuracies. Second, it's compare end-to-end with our reference systems. So now let's talk about the evaluations. So here is the dataset information. We use the G0 to G13 to represent the different dataset. So first, we show that our solution GRAPHPY achieves similar accuracy with the DGL. Then we show that our solution achieves significant performance speed up over DGL across different model and different dataset. So the last one is like a case study. We show that our solution GRAPHPY can help us to re-examine some GNN optimization techniques. So first is kernel fusion beneficial in GNN? So one prior work, DGNN, they used kernel fusion a lot, and they say that the kernel fusion can lead to the large memory saving and runtime speedups. So what we do is we compare the DGNN with our solution GRAPHPY. However, we find that the DGNN actually achieves 1.48 times slower than the GRAPHPY. And we also find for the memory saving, the DGNN can only achieve 6.4% memory saving compared to the GRAPHPY. So you can see, given all this like performance slowdown and modest memory saving, whether the kernel fusion is beneficial in GNN becomes open question. So yeah, so that's all. Thank you. Any questions?